Welcome, ladies and gentlemen. So what I'd like to do is show you how to determine all of the rational roots and then find all of the zeros, all of the real zeros and imaginary zeros, or roots of a polynomial. So basically, we have two equations here, and then we have a function. So basically, when we're dealing with equations, we're going to call them roots. And dealing with functions, we're going to call them zeros. But basically, they're mentioned the same thing. Now, the first question we wanted to address was finding all of the rational. Remember, rational are just going to be roots or zeros that we can write in rational format. And to do that, we're going to use the rational zero test. So remember, when using the rational zero test, we're basically going to make sure our polynomial is in descending order. And we're just going to take our p over our q, where q, again, represents the leading coefficient of each one of our terms. In this case, we both have 1 in all of them. Okay? So to do p over q, or to determine all of our rational zeros, again, remember, it's going to be plus or minus. Now, since 1's in my denominator, I'm not going to use 1. I'm just going to now list all of the factors of 12. So I'm going to have plus or minus 12, plus or minus 6, plus or minus 4, plus or minus, I don't need to keep on doing that, 3, plus or minus 2, and plus or minus 1. Okay, so those are going to be the list of all the rational zeros. But we're not just finding rational zeros. We're going to find irrational zeros, as well as determining all of the imaginary or complex zeros. But the first thing, the easiest thing to do, is to start off with, well, what are going to be the rational zeros? So the rational zeros tells us what are going to be the possible rational zeros. So if we have a rational zero, it's going to be plus or minus one of these numbers. Now, if you have a calculator, I would highly recommend that you take the function, plug it into the function, graph it, or use the table function to determine what the zeros are. However, if you don't have a calculator, for the first problem, I will show you how to do it without using a calculator. However, for the other two, though, I am going to assume you have a calculator and assume you can at least find 1 or 2 rational zeros without having to use synthetic division. But for right now, since it won't take me that long, let's pretend you don't have a calculator. So if I wanted to determine which of these rational zeros, because this is only a third-degree polynomial, that means there's only 3 zeros, or 3 roots. Well, I have a lot of roots to choose from, right? Plus or minus 1, 2, 3, 4, 5, 6 of them. I have 12 possibilities. So the best thing to do is to start testing which ones work and which ones don't. So the easiest thing to do is start with the smaller roots, and then just use synthetic division. So if these are my roots, that means that's what I'm going to use for my synthetic division. And I'm just going to do positive 1 and negative 1, because remember, it's plus or minus all of these. Now, when you set up synthetic division, notice that I don't have an x squared. So my coefficient for that is going to be 0. So when setting up synthetic division, I'm going to be 1, 0, negative 10, and negative 12. 1, 0, negative 10, and negative 12. Then I'm just going to test synthetic division here pretty quickly. We've already gone over this, so I'll try to do it a little bit quicker. Bring down the 1. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. Negative 10 plus 1 is negative 9. Negative 9 times 1 is negative 9. This gives you a negative 21. That is a remainder. So therefore, positive 1 is not a root of that equation. So now let's move to the next one. Let's try negative 1. Bring down the 1. 1 times negative 1 is negative 1. 0 plus negative 1. 0 plus negative 1 is going to be a negative 1. Negative 1 times negative 1 is positive 1. Negative 10 plus positive 1 is going to be a negative 9. Negative 9 times negative 1 is going to be a positive 9 equals negative 3. Again, we have another remainder. So therefore, those are not roots. That means you can't create a factor that's going to evenly divide with 1 and negative 1. So now we move to the next number, 2. And again, if you don't have a calculator, this is just the process you have to do. But I'm talking my way through it. You could obviously go through this a little bit quicker on your own if you're just doing synthetic division. So now I'm going to use 2. So I'm going to use negative 2, and I'm going to use positive 2. Doesn't matter which one you did. But once you see why I chose negative 2, you'll see why I put it over here. So again, set up the same thing. 1, 0, negative 10, negative 12. Let's do 2. 2. OK, so it's going to be 1, 0, negative 10, negative 12. So let's bring down the 1. 1 times negative 2 is going to be a negative 2. 0 plus negative 2 is negative 2. Negative 2 times negative 2 is going to be a positive 4. Negative 10 plus 4 is going to be a negative 6. Negative 6 times negative 2 is a positive 12. Add those together, 0. Hey, guess what? Negative 2 is a root of this equation. It's the same thing as like a 0. So I can write a factor from that. That means x plus 2 is a factor. You can evenly divide x plus 2 into that equation. Now, Notice that the power again is 3. There's 2 other zeros. Are they rational, complex, irrational? I don't know. Since I already set up 2, let's go ahead and do that. So I bring down 1. 1 times 2 is 2. 0 plus 2 is 2. 2 times 2 is 4. Negative 10 plus 4 is negative 6. Negative 6 times 2 is a negative 12. Negative 24. So 2 is not a 0. Now, you can go ahead and test 3, 4, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12 using the same thing if you'd like to. However, we don't know if the other 2 zeros are going to be rational. So we take this as our solution. Now, let's take our quotient and let's write this as a polynomial. So we start with remainder. That's our constant. That's our linear. That's our quadratic. So to write this as a quadratic, I'll write x squared minus 2x minus 6. Now, remember, this is a root. So basically, we can write this as x equals negative 2. So to write this as a factor, I'll set it equal to 0, and I'll say x plus 2 is equal to 0. So that means that is my factor. So technically, since this factor evenly divides into that, x plus this, my factor, times my quotient equals my polynomial. All right? However, if you were to set this equal to 0, right, and you were to use the zero product property, you'd set this equal to 0 and this equal to 0. Well, we already set this equal to 0. We know that equals negative 2. So I'm not going to worry about that right now. We already know that is a root. We want to find the remaining roots from this. And this is a quadratic. So hopefully you see in this case, a quadratic, it's either going to be factorable, or you're going to want to use completing the square or quadratic formula to find the remaining roots. So we look at this, and I say, all right, what 2 numbers multiply to give me negative 6, but add to give me negative 1? Unfortunately, there isn't any. So therefore, I need to use the quadratic formula, where the quadratic formula states x is going to equal plus or minus opposite of b. Oops. Sorry. Opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2a. Now again, what does a, b, and c represent? A represents the coefficient of x squared. B represents the coefficient of your linear. And c represents your constant. So now I'm just going to say, OK, in my case, a is equal to 1. B is equal to negative 2. And c is equal to negative 6. Now I'm going to plug them into the quadratic formula to determine my actual remaining roots. So therefore, I have x equals, opposite of b is going to be a positive 2, plus or minus the square root of negative 2 squared minus 4 times a, which is 1, times c, which is negative 6. Now, and this is all over 2 times 1, which is just 2. Now, I am running out a little bit of a room. So I'm going to do a little bit of math here together. So negative 2 squared is negative 2 times negative 2, which is positive 4. Negative 4 times negative 6 is positive 28. So I have 4 plus 28, or sorry, 4 plus 24 is going to be 28. 6 times 4 is 24. So I have x equals 2 plus or minus the square root of positive 28 divided by 2. Now, the next thing we want to do is, you could say, I mean, that is going to be your exact answer, but we can simplify this. I can break this apart. I can simplify my radical as 4 times square root of 7. So I'll write that as x equals 2 plus or minus the square root of 4 times 7 divided by 2. The reason why I do that is I can take the square root of 4, which is 2. So it's 2 plus or minus 2 square root of 7 divided by 2. Right? Square root of 4 is 2. You can't take the square root of 7. Then I can divide the 2 into both of these. So my final answer is going to be 1 plus or minus the square root of 7. So now, when we're looking into this, my zeros, or my roots here, I know that x equals negative 2, x equals 1 plus the square root of 7, and x equals 1 minus the square root of 7. Right? I would write it in solution set form, but you can see I'm kind of like ran out of space here. So I'm just going to list all of my roots or zeros, roots of this equation, or zeros if it was a function. OK. So that's basically it. All right. So in these cases, we're all going to use quadratic formula. You can see how that kind of took me a while. So I'm going to kind of speed up the process here. I still want to find our rational roots, all right? And I'll explain that here in a second. So let's go ahead and find our rational roots here. I'm going to kind of go through this a little bit quicker. Again, we're going to take our p, our roots, factors of p divided by q. So this one's going to be plus or minus 4, 2, 1. Now again, this wouldn't be too bad. Check plus or minus 1, check plus or minus 2, and check plus or minus 4. However, I did a little research, and I graphed this myself. Rather than doing what I did before and checking them all, I determined that 2 and negative 2 are zeros. Both of them are rational zeros. OK? So what I'm going to do is I'm going to use synthetic division with both of those roots to keep on finding my factors. So the first one I'll do is positive 2. Yeah, I'm kind of running out of space, so I'll use positive 2. Now again, you're going to use synthetic division. Make sure it's in descending order. So I have 1, negative 2, negative 5, 8, and 4. Bring down the 1. 1 times 2 is 2. Negative 2 plus 2 is 0. 0 times 2 is 0. Negative 5 plus 0 is going to be a negative 5. Negative 5 times 2 is negative 10. 8 plus negative 10 is negative 2. Negative 2 times 2 is negative 4, which gives me 0. Now, here's where it gets confusing. Or not really confusing, but here's where a lot of students make a mistake. This is a factor, right? I can write this in my quadratic form. However, I noticed that not only is 2 a factor, but also negative 2 is a factor. So it's kind of like saying 2 is the factor of 12, right? Well, what else is a factor of 12? 3, right? So if I want to find the smallest factors of 12, if I just take 12 and divide it by 2, I get 6. Well, 6 is not a prime number, right? I can divide that again by another factor, which in that case would be like 3. You can keep on dividing those down. So this factor, yes, this is a factor of that. But this is, if I was going to write this in my factored form, that would be my remainder, constant, linear, quadratic, cubic. I still have a cubic factor. I can't use quadratic formula on a cubic factor. I could factor it, but in this case, this is non-factorable. So therefore, I'm going to want to keep on using synthetic division until I get a factor that I can actually, that is factorable. It's in quadratic form or linear. So since I know negative 2 is a factor, what I'm going to use is I'm going to use synthetic division again. But rather than going back to my original coefficients, I'm now going to go to the coefficients of my quotient of my other factor. So I'm going to use 1, 0, negative 5, negative 2. OK? I don't need to go back and use these. I'm going to use this quotient. Because if I go back and use this, that's like saying 12 divided by 2 is 6, and 12 divided by 3 is 4. Right? But they're not going to give you, you've got to keep on factoring them down. They're just going to give you different factors. So now let's take our previous coefficient and then divide it using synthetic division by our other factor, which again I found by graphing the polynomial. So I bring down the 1. 1 times negative 2 is negative 2. 0 plus negative 2 is negative 2. Negative 2 times negative 2 is a positive 4. Negative 5 plus 4 is going to be a negative 1. Negative 1 times negative 2 is a positive 2. 0. So now I have 0 is my remainder, which tells me that negative 2 is a factor of this factor and of that factor, right? If 2 goes into 6, then 2 also goes into 12, because 6 and 12, or 6 is a factor of 12 as well. So that is going to be my constant, linear, quadratic. So if I write this in quadratic form, I can see if it's factorable. So I have x squared minus 2x minus 1. So what two numbers? So if I want to factor this, right? This is basically this times x minus 2 times x plus 2. But here's my other factor. I want to keep on factoring this down. I already know these are my zeros, right? We're dealing with the function. These are my two zeros. So I want to keep on factoring this down. I don't have another rational 0 to keep on factoring this down with. So I want to determine, is it factorable? What two numbers multiply to give you negative 1, but then add to give you negative 2? Unfortunately, it doesn't work. Negative 1 times negative 1 does add, or negative 1 times negative 1 gives you a positive 1, even though they add to negative 2. So I have to go back and use the quadratic formula. I broke down the quadratic formula and what a, b, and c are. So now I'm just going to plug them in for this one, because hopefully quadratic formula is a little bit familiar for you. So I'm going to do x equals opposite of, oops, not opposite of b. Opposite of b, which is 2. So that's going to be a positive 2, plus or minus the square root of b squared, which is negative 2, squared, minus 4 times a, which is 1, times c, which is negative 1. all divided by 2 times a, which is 1. OK. So I have 2 plus or minus. Now let's, again, kind of simplify this. Negative 2 squared is positive 4. Negative 4 times 1 times negative 1 is going to be a positive 4. So I have 4 plus 4 is 8. So square root of 8, then divided by 2. Just like I simplified the square root of 28, I'm going to simplify the square root of 8. When doing that, x equals 2 plus or minus 2 square root of 2 divided by 2. Then I can simplify these, divide the 2 into both of those, and I'm left with 1 plus or minus the square root of 2. So now my solution set, which is getting kind of crazy here, I'm going to kind of fit it in. So now we know x equals 2, x equals negative 2, x equals 1 plus the square root of 2, and x equals 1 minus the square root of 2. So notice, again, I didn't pay attention to the last one. Notice how many zeros we have. 1, 2, 3, 4. What is the degree of our polynomial? 4. However, only 2 of those zeros were rational. But it's important to know what your rational roots are so you can use synthetic division. How many zeros do I have here? 1, 2, 3. What is the degree of my polynomial? 3, right? But only one of my answers was rational. The other 2 are irrational. All right, so let's go into the last one. Again, I'm going to use my rational zero test, p over q. So I do p over q plus or minus. The factors of p over q, again, q is 1, so I'm just going to list the factors of 15. So it's going to be 15, 5, 3, and 1. OK? Now again, rather than checking with synthetic division, this video is already long enough, I used my calculator. And what I determined was negative 1 and 3 were zeros. So I have 3. So 3 was a 0, and negative 1 was a 0. OK? I just looked at the graph, saw where it crossed the x-axis, and those are my 2 zeros. So now we're going to use synthetic division. Notice, again, synthetic division, I'm missing x cubed. So I have to use a placeholder for that. So I'm going to use synthetic division for 3. It doesn't matter which one you start with. So I'm going to use 1, 0, negative 2, negative 16, negative 15. Now let's use synthetic division. Bring down the 1. 1 times 3 is 3. 0 plus 3 is 3. 3 times 3 is 9. Negative 2 plus 9 is going to be a positive 7. 7 times 3 is 21. Negative 16 plus 21 is positive 5. 5 times 3 is positive 15. 0. OK. Again, we have now another zero. We have another quotient here, which is another factor. I could look at it and see if it's factorable. So that's remainder, constant, linear, quadratic, and cubic. So I could say x cubed plus 3x squared plus 7x plus 5. All right, it's 4 terms. Is that factorable by grouping? Unfortunately, no. So to solve this, I want to get this down to a quadratic where I could factor it or use quadratic formula. So now I know that negative 1 is another rational 0. So I'm going to use negative 1 as my other rational 0. And again, I'm only going to take the quotient. I'm not going to go back to my original problem. I'm going to go back to the quotient to further factor it down. So it's a smaller and smaller factor. So I have 1, 3, 7, 5. So I bring down the 1. 1 times 1 is negative 1. 3 plus negative 1 is positive 2. 2 times negative 1 is negative 2. 7 plus negative 2 is going to be a positive 5. 5 times negative 1 is negative 5. 0. OK, so I have remainder is 0. That means that, again, confirms that that is a factor. This is my constant, linear, quadratic. So to write this as a factor, it would be x squared plus 2x plus 5. So I want to see, is that factorable? What 2 numbers multiply to give you 5 but add to give you positive 2? It's not factorable. So therefore, again, you're going to want to solve for this. You could use completing the square or quadratic formula. Let's use, again, quadratic formula. So to do that, I have x equals opposite of b, which is going to be a negative 2, plus or minus the square root of b squared, which would be 2 squared, minus 4 times a, which is 1, times c, which is 5. And that's all divided by 2 times 1, which is 2. OK, so negative 2 plus or minus. Let's do this. 2 squared is 4. Negative 4 times 5 is a negative 20. So it's 4 minus 20, which is going to give me a negative 16. And that's all over 2. Now, in these two cases, I couldn't take the square root of the numbers, right? I had to simplify them. Here, you can't take the square root of negative 16 because it's a negative. But we can use our imaginary unit to take the square root of negative 16. So what we can do is we can rewrite this as x equals negative 2 plus or minus the square root of 16 times negative 1 divided by 2. So now, the square root of 16 we know is 4. The square root of negative 1 is I. So that equals negative 2 plus or minus 4I divided by 2. Again, divide the 2 into both of those, and I'm left with a negative 1 plus or minus 2I. So going back to my solution set, I have barely any room, but we know that 3 is a root. Negative 1 is a root. It's a root because it's a root, again, because it's an equation, not a function. If it was a function, we'd call them zeros, but whatever. They're the same thing. X-intercepts, solutions. So we can say x equals 3, x equals negative 1, and then x equals negative 1 plus 2i, and x equals negative 1 minus 2i. Again, notice how many zeros do I have? 4. What is the power of my function? 4. I had 2 rational. And instead of 2 irrational, I have 2 complex roots. Okay? So knowing that you have rational roots is very helpful. But it doesn't mean all of the roots or zeros are always going to be rational. But it's important to know what they are, so you can either test them using synthetic division, or if you already know what they are, you can use synthetic division to get your factors down to quadratics, where they're either going to be factorable with more rational roots, or they're going to provide irrational or complex solutions. So there you go, ladies and gentlemen. That is how you find all of the zeros, roots, solutions, x-intercepts of a polynomial. Thanks.